Today's episode is on color perception. In previous episodes, we discussed the color gamut and how we can dilate and move it in the same way we can dilate our state space. A similar concept also exists in resource theory, in which we can warp our state space like we would a color gamut. In this video, we will start by thinking of color in terms of skew. This also means thinking of color as a probability density or probability mass function. On such a model, the color we perceive would then be represented as a wave of probability. The skew of the distribution would then help display how much of that specific color is likely to be perceived by the eye during our data sampling. But how was this discovered? It started when Thomas Young wanted to see how different colors were detected by the eye. Rather than using a Newtonian color wheel or the later invented 1931 color space, Thomas Young had to improvise. He decided to use something along the lines of a probability density function, as mentioned earlier. Operating on limited data about light, he came up with this representation. Using the data he collected, he hypothesized 3 different cells that detected color. In the Thomas Young model of trichromaticity, we presume there is a cell that mostly catches the red area of the spectrum, a cell for the green area of the spectrum in the middle, and an additional cell for the blue side of the spectrum. This corresponds with long, medium, and short waves respectively. You might notice that both red and blue have tails to their distributions. Red is right-tailed, whereas blue is left-tailed. Green, on the other hand, has more of a Gaussian or normal distribution centered around the middle. With the Thomas Young model of trichromaticity, if the distribution has values that are more concentrated on the right side, the distribution will start to look blue. There are plenty of occasions in modeling when the difference between left and right depends on nothing more than the scale you want to employ. We discussed this in our episode on financial skew. This means we can just call it blue-tailed and red-tailed, since left and right are rather arbitrary here. Blue is red-tailed and red is blue-tailed. Now we can flip the model whichever way we'd like without having to change our terminology every time. These 3 hypothesized cells are why we call the data on Thomas Young's chart tri-stimulus values. These cells are stress-strained in order to perceive color, which ties into other concepts that Thomas Young worked on. You can learn more about stress strain in our episode on it. The ramberg-osgood equation uses something called Thomas Young's modulus to help model stress strain. This relationship is also why funny colored glasses might cause you to see differently when you take them off. The cells in your eye are still stress strained, and as such, your color gamut has been distorted. Later scientists would move on to the 1931 CIE lab color space, but the work of Thomas Young translated well onto this new model. The 3 RGB cells of Thomas Young are represented by the RGB triangular gamut of color space. Green takes up a large amount of the map. Red and blue sit enshrouding the line of purples, while the seemingly Gaussian distribution of green stretches out over a wide portion of space above. There are other interesting details hidden in color space, more reminiscent of Thomas Young. A color space is often considered to be made up of a gamut, a model, and sometimes a transfer function. We can conceptually dilate or move the gamut by including more subtle differences of a color within our color model diagram, or constrict it by ignoring said differences. We can also take a more physical approach with funny colored glasses, in which we exhaust our eye's ability to perceive a specific range of color. In doing so, we mutate the appearance of how the data would be represented on Thomas Young's model. The color range that we exhaust would shrink, as the color range we are left with might be represented as growing on that side of the distribution. Since the color space is just a representative tool, there are many ways we can abuse it to get our point across. We can either change the gamut or the diagram of the color model itself to represent a mutation in our representation of color. Some color scientists get very annoyed when you mess with the color model diagram rather than changing the gamut, and would be very humbled to realize that McAdam was the one who originally did this. If we were to instead change the gamut to represent a color filter, then it might no longer look like the RGB triangle we are most familiar with. For example, a color gamut portraying a blue filter might have the shape of a tin teardrop while maintaining an unchanged color model diagram. Changing the color gamut is more traditionally correct as a representation of a color filter rather than fooling around with the color model diagram. However, other color scientists might claim that this is all just a language game anyway. If we were to focus on the differences in green and represent it as a change in the diagram, green would take up more of the underlying space of our color model. McAdam was the first to make this point with his artistic representation of the McAdam ellipse. Rather than a tin teardrop, it looks kind of like a squid eating dough in a polyethylene bag. Joseph Albers, McAdam, and many other scientists have worked to show how color is relative. After all, if you're wearing rose-tinted glasses, then the world might look a bit different to you when you take them off. Now, let's set aside that Young model for something more mature. The spectral power distribution. Instead of just looking at wavelength and stimulus values like in the Thomas Young model, we look at power per unit area per unit of wavelength of the entire electromagnetic spectrum. We can see a change in the height of the shape as color shifts with the strength of the blackbody radiation. In the context of blackbody radiation, red is lower in Kelvin, lower in frequency, and closer to ground state. Whereas blue has a much higher temperature and higher frequency. You can see this when you adjust the flame of your blowtorch. Here, you'll notice the differences between lilac and hibiscus. Green is still right in between both of them, as expected, but it doesn't exactly show up well in blackbody radiation due to how far away the Planckian locus is from green on the color gamut. As something gets hotter, it tends to become more blue. Its spectral power distribution increases, along with the frequency and energy state. Now, if we were to look at Thomas Young's model, it shows us a red-tailed distribution. After all, blue is red-tailed, and red is blue-tailed. In other circumstances, our model will diverge from reality. This is known as a tail-end event. Once you start thinking in terms of negative and positive skew, you are thinking in terms of left versus right, or blue versus red. 1931 color space isn't all that accurate and doesn't show everything involved in vision. Within your measurement of skew can be a representation of everything from time to tone, to scale to temperature. As a moment of order, skew is especially difficult and never tells the full tale, especially when the distribution has exotic moments of order. Thank you.